In this example, we will minimize cost for multiple outputs. Donatello has a firm that produces two goods: Good Book Cosmetics and Rhapsody Perfumes. Due to a government quota by President Voldemort, the firm must produce subject to this constraint. Here we have the cost function. In this example, we need to find the optimal output combination that minimizes the cost, and also we need to find the optimal cost. But in this particular example, we will use the Kramer's rule to solve the first order condition equations. The reason of why we will use the Kramer's rule, you will see it when we will start solving the first order conditions. Here we have our cost minimization problem, in which we have the cost function subject to this quota constraint. But remember, in order to set up our Lagrange function, which is equal to the objective function minus lambda times the restriction, we have to have one of the sides equals to 0 for the restriction. So here we have our constraint. So in order to make 0, for example, the left-hand side, we can subtract x and y from both sides. So here we have 0 equals 42 minus x minus y. So this will be the restriction. So in that way, we are subtracting nothing to the objective function. Our Lagrange is then 8x squared minus xy plus 12y squared minus lambda times 42 minus x minus y. This means that the Lagrange function has as variables x, y, and lambda. Now, let's compute the first order conditions. For the case of x, this is 16x minus y, this is 0, minus lambda times the only part that has x is minus x, so the derivative is minus 1. And we set this equals to 0. With respect to y is minus x plus 24y minus lambda times, here also we have only minus y, so the derivative with respect to y is minus 1. So this is equals to 0. And finally, the derivative of the Lagrange with respect to lambda. Here, derivative of lambda with respect to lambda is 1. So negative 1 times 42 minus x minus y, and also equals to 0. Before we continue, notice something interesting. All these variables, when we simplify them, all of them are linear and they do not combine each other. So for example, here we don't have any xy's. So there is no xy combinations. There is no x squared or y squared or 1 over x or anything. Everything is linear. To see that clearer, let's simplify here this. So this is 16x minus y plus lambda equals 0. Here we have minus x plus 24y plus lambda equals 0. And here we will have x plus y, and then minus 42 will go to the other side as positive 42. So as you can see here, everything is linear. So we can use actually the Kramer's rule. So let's copy this into the next page. Something pretty important that you need to remember is that you always need to move the constants to the right hand side. And this is because we will need to express it in the matrix form when we want to use the Kramer rule. And as you can remember, the vector of constant is always in the right hand side. Now let's identify here the vector of variables. Here we have x, y, and lambda. The matrix of coefficients is 16 minus 1, 1, minus 1, 24, 1, and 1, 1, and 0. And the vector of constants will be 0, 0, and 42. Notice, if you forget to move the right hand side constant, then you will have a problem because the vector of constants will be all 0 and you cannot solve that problem. Because we have three variables, we will need three submatrices. The first submatrix is the matrix A, except that the first column is replaced by the vector of constants. Then A sub 2 and A sub 3. Now remember, in order to obtain the value of x, because this is the first variable in order, this is the determinant of A sub 1 divided by A. For the case of y, will be the second submatrix. And for the case of lambda, we will use the third submatrix. So let's find the determinants of each of the four matrices in a separate page. To obtain the determinants of each of these four matrices, first we need to copy the first two columns to the right hand side of each of the matrices. So let's do that. Let's start with the multiplications of the main diagonals. So this is 0 plus negative 1 and also negative 1. So this is going to be negative 2. Let's proceed with the anti-diagonals. So this is 24 plus 16 plus 0. So this is 40. This means that the determinant of A is minus 2 minus 40 minus 42. Let's continue with the submatrix A1. this is 0, this is minus 42, and this is 0. So this is minus 42. Now, 42 times 24 times 1 is 1008. 1 times 1 times 0 is 0, and this is also 0. So the determinant of a sub 1 is equals to minus 1050. For a sub 2, we get 0 plus 0. 1 times minus 1 times 42 is minus 42. Here we have 0. 42 times 1 times 16 is 672. And this is 0. This means that the determinant of a sub 2 is minus 714. Now let's continue with a sub 3. 16 times 24 times 42 is 16,128. This is 0 and this is 0. From the anti-diagonals, this is 0, this is 0, and this is 42. This means that the determinant of a sub 3 is 16,086. Let's put these values on the previous page. And now we can obtain the values for x, which is minus 1050 divided by minus 42. This is equals to 25. For the case of y, this is minus 714 divided by minus 42. This is equals to 17. And then for the case of lambda, this is equals to minus 383. This means that the optimum combination is x equals to 25 and y equals to 17. And something that you can check in this particular case is that if you sum both, this is equals to 42, which was the restriction. The last step is to find the optimal cost. Here we just need to replace the values of x and y in the cost function. And here we obtained that the cost function, the optimal value is $8,043.